Hi everyone, let's get going. So I know you're all excited about the test. I know you're not, but Thomas will come at the end. Let's not, well, I discussed it last time, but for now just take a look at it, talk to these guys. If there's anything to fix, we'll fix it. There is enough time to adjust things if needed. Then I'll take a look at the actual average, because what I have now is just now, and decide what to do, okay? As I've done last time, pretty much. As of now, the average is lower, even though I think we're counting zeros, right? Well, zeros are basically people not showing up, so they don't count. So that's probably why it's lower, because there's some people didn't show up. But don't get too worried about that. We'll figure it out. So I hope at this point it's clear that the way we've been doing things is the homeworks are hard work. The test is not supposed to be, because we have 50 minutes. I repeated this several times. And one of my postdocs in the lab told me, when your professor tells you, don't overthink it, it's like your wife telling you, yeah, everything is fine. You just don't believe that person, right? But in this case, I'm not being your wife, okay? I mean what I say. Do not overthink it. If you sit down and you're starting to spend too much time on a question, maybe there is a simpler way to address it, because it's 50 minutes. I can't ask you to do what you do in 2 days in 50 minutes. What you do in 2 days develops the knowledge that should trigger, oh yeah, I've seen this, I've done it in my code, or I've done something similar on a piece of paper before putting it in MATLAB, again, if you have done it yourself. So, but anyways, we'll talk about them. It's time to start with these, and by the way, Gauss variational equations, which are not in the book that some of you may be using, because the one online is the second edition, and it doesn't even have a chapter on that, so I gave you the chapter. Okay? So a chapter 12 is what you don't have in the online version, but you have it on Canvas. Now, what are these? Now, today I'm going to just show you how you find one of these equations. To prove all of them will take me probably 2 weeks, and I'm not going to waste our time that way, because you need to know where they come from, what they mean, how to use them. So we'll, do a lot of calculations one day and then look at them and use them. So this is what we started from again, and we said, well, this is not enough because nature is not working this way. There is usually something else here, and this could be J2, which we have demonstrated last time. This could be the drag. This could be J2 and the drag. This could be J2 and the drag and the solar radiation pressure and your turning out thrusters. Whatever you want goes in here as an additional acceleration. Now, if you only take these into account, your semi-major axis, your eccentricity, your inclination, your right ascension of the ascending node, your argument of perigee, these 5 remain constant, okay? While, of course, the true anomaly is changing, is your position on that line, if everything is ideal. Now, this additional term makes all of these guys vary, as you have seen in your homework, I believe. And so we want to find these equations that are basically differential equations. Actually, let's be thorough here. First order differential equations for the osculating orbital parameters. Okay? And osculating again is you have position velocity right now, convert into orbital parameters. Then in the next time step, you're probably going to get a different combination of these, because you have more than just this attraction. And so what you have actually done is the following. Let's call U a generic orbital parameter. So what we know it's true is that this U, it's, the way we have done it already in the homework, it's a function of position and velocity. Every time I give you 3 component vectors like that, position and velocity, you can compute all of these, right? Well then, what I want to find are those differential equations. So I would like to find for each of those orbital parameters something like this, an expression for du dt. And since this depends on position and velocity, it will imply that we do du in dr dotted with dr in dt plus du in dv dotted with dv in dt, where these are dot products. This is obviously a vector, is derivative of position. This is a vector, derivative of velocity. Now, a guy like this, where I have a scalar partial with respect to a vector, it's basically going to look like this. Partial of u with respect to, say, r on the I-axis, I, plus partial of u with respect to r on the j-axis, j, plus partial of u with respect to r component on the k-axis, k. That's what it means. So that's why these are two dot products, okay? Now, if I continue here, I'm going to notice a few things that I can use for my following calculations. This remains as it is, but that dv in dt, what is that? Well, that is my r double dot, right? That's what it is. And so if I have something like that, I can substitute minus mu over r cubed r plus the perturbation. Again, whatever that is. I don't know what it is. It's there. And so if I collect all the things where the perturbation does not appear, this expression is going to look like du, partial of u with respect to r, dotted with time derivative of r with respect to time, plus partial of u with respect to v, dotted with this Keplerian force here, force per unit mass, of course, plus partial of u with respect to v, dotted with p, right? I just broke this in two pieces. Well, p here doesn't appear at all. There's no perturbation there, right? So what this is actually, this is the rate of change in time of that orbital parameter. Again, u for us could be a, could be e, could be I, any of those six. This is basically your rate of change of u when you have just Keplerian acceleration. And by Keplerian, I mean the ideal initial force that we have been using, minus mu over r cubed r, no perturbations. And so really the piece we need to focus on is this one. And this is a dot product of two vectors that we have to resolve in some coordinate system. Now this thing here, if I'm looking at those six orbital parameters, I know already what they are. What is the rate of change of the same major axis when I have a Keplerian orbit? 0. What is the rate of change of eccentricity? 0. I, 0. Omega, 0. Big omega, little omega, 0. What is the only one that is not 0 is this one. And what is this? Remember? We can prove it again if you want. But it's h over r squared. That's what it is. Because this is changing. The true anomaly is increasing. It's not constant. Otherwise, your satellite is just sitting there on top of you, going nowhere. Do you want me to prove this again? It comes from the fact that we broke the velocity into a v radial, u radial, plus v perpendicular, u perpendicular. And if you use this, your h vector is r crossed with v. Oh, by the way, this also means r dot ur plus r theta dot u perpendicular. Go back to lecture probably number 1 or 2. We looked at an exercise like this. And so when you cross r with this vector, you're left with basically r crossing, let's see, r theta dot u perpendicular, which is r ur cross with r theta dot. I'm making a very short story too long here. It's r squared theta dot u, basically let's call this uh, is the vector that points like h. So compare this with this, and you can show that that's what you get. D theta in dt is theta dot, okay? Make sense? So the only one that doesn't change, that does change is theta. And so what we have to find is basically those du dv. So I have to find how these scalars that are the orbital parameters change, well, what are the partials of them with respect to the velocity vector, and then dot that with whatever perturbation I have. And I'm only going to do it for one case, also skipping some steps because it takes a long time, but it does entail everything that we have seen so far. So just in case it's not clear, you can't forget the things that we have seen. Okay, before I do that, coordinate systems that we have used so far. We have used ECI because those equations that I'm going to give you are resolved in a particular coordinate system, which is very convenient. So this is the typical, one that we have used from basically day one. Inertial, as far as we are concerned, x is pointing to the line of equinoxes. Then you have y. Z is the rotation of the axis of rotation of the planet. So that's my coordinate system fixed in ECI, right? And then we said, if this is my orbit, and say that it does have, so this is my attracting planet, it does have an eccentricity, or if it doesn't have an eccentricity, just pick your R0 as the direction of a fake eccentricity, because the vector doesn't exist. But you need to decide which line you're going to use to count your true anomaly, right? At some point you will have to decide some line, even if you don't have an eccentricity. So this is theta, say that this is the position of the spacecraft on some orbit. And we said the perifocal frame will be defined as, what did we use? The direction of the eccentricity, let's call it P unit vector. This is not P the perturbation, okay? It's just usually called P. Let's call W the vector that points like H, normal to the orbit. And then with the cross product, you complete with Q the right-handed coordinate system. So in other words, the second one, which is the perifocal, is going to be with P, that is the vector E normalized, W is the vector H normalized, and then Q is W cross with P. Then there is another one that we have actually used already, but I'm going to just change the name of it just to be consistent with what people do in books. So if this is my spacecraft, I can define, as we have done already, a direction which is the radial one. And instead of calling it UR, then I'm going to just call it R with the hat. I'm going to recycle W. Okay? And then the cross product of the two gives me what I call the U perpendicular, but I'm just going to call it S. What that is called actually is local vertical, local horizontal. So it's you looking straight up at the planet that gives you the R direction, or the x-axis if you want. The normal to the orbital plane is W, or the Z. The Y is what completes that right-handed coordinate system. So in that case, R unit vector is, of course, R normalized. I'll tell you why I'm spending time telling you this. W is, again, that, no news. And S is W cross with R. And you do know how to go now from ECI to one of those, and vice versa. You have the 3-1-3 rotation to go from a vector in ECI to a vector into the perifocal frame, and then add an additional theta rotation if you want to project that vector in LVLH. But I'm not going to be, yes?
Is the W literally the same variable?
Yeah, it is. Yeah, it is.
Okay.
Yeah, that's recycled. Yeah, it's the normal to the orbital plane. So those Gauss variational equations that we're going to find will be such that the perturbation P, the vector there, will be projected in these spaces. And the reason should be kind of intuitive. If you are going with your spacecraft and you are maneuvering, you're turning on a thruster, that creates a perturbation, and it's probably easier to see that perturbation projected in something that is flying with the spacecraft. Imagine trying to do that in ECI. The spacecraft is going around like crazy, and you're trying to project in ECI. That's going to take a rotation matrix at every single instant, while you may just have an easy way to project that thrust in LVLH. Even just the perturbations that you get from J2 or drag, you may have very precise accelerometers on board that measure those, but those devices are strapped on the spacecraft. This is not the body-attached reference coordinate system, but it could be. You could have a spacecraft that is flying stabilized in that basis. We're not doing attitude here. but it will definitely be easier to find those perturbations in LVLH. And next week, I'll start talking about relative motion. I'm changing a little bit the order of the topics here, but I do want to do relative motion and rendezvous, because that's what we are doing when we go to the ISS. And that's what you use. You use that, the LVLH. You're sitting on your spacecraft, X is in one direction, Y is the other direction, Z is normal, and that's how you look at the motion of a spacecraft that it's approaching you when it's going to dock, for example. Yes?
What does LVLH stand for again?
Local vertical, local horizontal. Yep. Okay, so just introducing what I'm going to do next. I'm going to compute the Gauss variational equation again without spending too much time on too many details for the eccentricity, just for fun. Just to show you how involving it is before we look at all of them, and show also the effect of drag still on the eccentricity. Just because, again, it will take me one lecture for each one of them, and that means 6 lectures, and it's definitely too much time. Okay, what is the eccentricity? The eccentricity vector, to begin with, it was 1 over mu, cross product of velocity and the angular momentum, minus mu, the normalized version of the position vector. Now, if you take this, dot it with itself, take the square root, you're going to believe me, I said I was going to skip some of the steps. This is what you get. It shouldn't take too long to prove it, but this is what it is. H squared over over mu squared v squared minus 2 mu over r. Okay. So what I need to find to have my Gauss variational equation is this. The rate of change in time of the eccentricity is going to be the rate of change in time of the eccentricity due to Keplerian acceleration, which means 0, plus that, in this case, is dE dV dotted with P. And since I decided that I was going to use this basis, P will be some generic perturbation that I can express as PR in the direction R plus PS in the direction S plus PW in the direction W. As we'll do today, if we talk about drag, for example, and you neglect the rotation of the planet, the atmosphere around the planet, this is pretty convenient. Basically, your drag is going to be only in plane. There's no W component. There's a lot of cases where flying with the spacecraft in terms of vectors is more convenient, of course. Okay. Now, a few things that we need to know to do these calculations are these. The partial of v squared with respect to v vector, I'm just going to do the first one. This implies doing the partial of, bless you, vi. Say that I'm working in some ijk basis. vj squared plus vk squared. This is going to be partial with respect to vi on I plus similar terms. And as you can imagine, the partial of this with respect to vi is 0. Same here. This is the only one. It gives you 2 partial of vi with respect to vi. So in the end, you get twice the velocity vector here. So that is one thing we can use. And then the same way, with a few more steps, you can prove these. They're going to be used there. See, I have v squared, I have h, so I'm going to use this. Let's see what this is. This is 2h cross with r. So we just know that applies, and we're going to use it. Any questions up to this point? Is it clear what I'm doing, except all the mathematical steps that may be more or less obvious, but it's algebra? Okay. The goal in the end for Gauss variational equations is finding these things. The partials of your orbital parameters with respect to the velocity vector. That's what you have to find. And then P will be whatever you need to plug in. It's J2 perturbation, drag, anything. Okay. So if I start doing that, dE dV, I see a square root here of this. So I'm definitely going to have 1 over 2, the same square root down here. So this is going to be E again, right? And then I have partial of, with respect to V, of what is inside the square root, which is h squared over mu squared v squared minus 2 mu over r. Okay? Let's see. 1 over 2 E. So if I use those two relationships down there, substitute here for the partial of h squared, you're going to do basically partial of this that multiplies this, and then this that multiplies the partial of this with respect to v. You're going to get, am I losing anyone? Everybody? Yes, everybody? Okay. You want me to just skip to the end, really? You don't want to suffer not even for one? It's just one. I'm not going to do the 6 of them. And I spent time to make my notes here. Why do I have them at this point? Of course, I'm not going to memorize this stuff. This would be crazy. But is it clear what you have to do? For each Gauss variational equation, you have to find this. The partial of that scalar, which is the orbital parameter with respect to v. And then what you're going to use is all the expressions that we have available. Everything that we have seen. The radial velocity expression, the tangential velocity expression, and other things.
What exactly are you
I am trying to find this. This is my goal. I want to find an expression for this. Yep. Basically the standard expression that everybody is using in astrodynamics. That's what I'm going to find.
Does that in words?
Hmm?
Can you like explain like what the partial of this is divided by with respect to the
Yeah, sure. What it is telling you, see it this way. If you want to have a words explanation, this is what it's going to give you. That dot product right there, partial of E with respect to V, dotted with P, you can look at it this way. This is your perturbation. Whatever acceleration is acting on you that you are creating because of thrusters, or unfortunately you're flying through that environment and you have to live with that. This is dotting, so this is a 3-component vector, this is another 3-component vector. So each first component of this is going to dot first component, times first component of this, second, third, and you get a scalar. So this thing in front of P, it's almost, I've heard people defining it as a measure of how much this acceleration is going to, how powerful is this acceleration in terms of changing this orbital parameter in particular. And you're going to have the same thing for A. dA, dt is going to be the partial of A with respect to V dotted with P. These are all 3-components vectors. They may be more or less, intense in terms of magnitude. They're going to give you how much this transforms itself into a quick or slow change of that particular orbital parameter. Say that dE dV, for some reason at a certain time, ends up being, I don't know, 1, 1, 1. That means that whatever is your perturbation, it translates into directly dE dt. So it's an efficiency of how much you can, if that's actually a desired perturbation, if this is a thruster, is how much the thruster can quickly allow you to change the orbital parameters as you want. The other side of the coin, if it's a perturbation, how annoying that perturbation is in altering your orbital parameter. Yes?
I noticed that, so once you have that dE dt, you still have to integrate that to get...
Well, yeah, all these differential equations. Well, there are several uses for these differential equations, and it was going to take a few lectures here. But the first one is, yes, you can directly integrate those and get the evolution of the orbital parameters as an alternative. But also, once you look at them, you can tell if an acceleration in a certain direction is going to increase or decrease that particular orbital parameter. Then next time we're going to look at the average effects that these perturbations have. They allow you to design sun-synchronous orbits, for example, which so far I just gave you a simulation and showed you that that's sun-synchronous. But it has to do with this particular Gauss variational equation. If you look at this one, the form that it will have, when you have J2 as the perturbation, then you can tell, okay, if I put my saddle in a certain configuration, it's going to, that d omega dt is going to change at a rate that I want. So they are a way for you to see what is directly the effect on orbital parameters of the perturbations, because so far we have no idea. I just integrate the Cartesian equations of motion, x, y, z, and then maybe convert those into orbital parameters. But ahead of time, I can't tell if I'm pushing in the LVLH s direction, what is that going to do to my orbital parameters? I don't know, right? Okay. It's only a couple of pages. It's not that long. It's not that long. Come on. Let me finish this one. Otherwise, I wasted my time. Okay. Let's see what we have here. Where I am here. Okay, this one. Mu squared over E h squared v plus v squared minus 2 mu r h cross with r. Okay. I think I'm missing a few things here. No, everything is fine. So this is just taking, what have I done here? I have taken this mu squared, is collected outside, and just divided by, simplify the two. It's the same exact expression. Now, v is what? V vector is vr r plus vs s, of course, if I use that basis, LVLH. And h cross with r, if I use the same basis and you do your calculation, it's basically hrs. Because this is h norm w cross with that vector. Okay? I'm sorry, with the r vector, r. And that's what you get. If you substitute those two, wherever you see v, you're going to see this, mu squared e. Okay, let's see, if you put everything together, h squared vr in the r direction, plus hr v squared minus 2 mu over r plus h squared vs, and this is in the s direction. I have taken those expressions right there. Wherever you see a velocity vector, you just substitute this. Where you see h cross r, you substitute this, hrs. Collect the terms that are in the same directions, r and s, and this is what you get. We're almost done. But we're going to do another substitution. What is vr? And what is vs? We have this, right? This is h over r, and this is one of the first things that we have seen. This expression here, remember? This is h. You remember these two? Radial velocity, tangential velocity, right after we've proved the Keplerian expression for an orbit. So if you use these and plug them in there, last steps, r plus h mu e squared. So the last test will be prove all the Gauss variational equations. How about that? You like it? No, I don't either. This is terrible. Okay. Promise, I'm almost done. I need to show you at least one. I need to show you how every single thing pretty much that we have done so far goes into finding these. And people have found them for us, so we don't. Okay, if you start from these expressions here and you put them together, you say that v is the square root of v radial plus vs squared. You're going to get that v is mu over h square root 1 plus 2 e cosine of theta plus e squared. Remember that this is r, because I haven't used this yet, so I'm going to use it. This allows me to say that e cosine of theta h squared mu r minus 1. Plug it in here. Your velocity is going to be 2 mu over r minus mu squared 1 minus e squared 1 over h squared. Go back and look at this at home. Don't do this at home, right? Okay. H over mu, I'm done. This is the last one. So if you use that expression that I gave you there for v, this is what you get. Whew. Okay. Yeah, I think that's it. So after all these painful calculations that we have done very quickly, this is going to tell me how E changes, what is the partial of E with respect to V. That's what it is. So you take this is a vector, right? If you wanted to finally tell me what is the effect of a perturbation on the eccentricity, whatever that is, this is what you do. You take that vector, so you want to find this in the end. You take that vector, dE dV that I just computed, and you dot it with P. And this is going to give you what? Well, it's going to give you the final Gauss variational equation for the eccentricity. Because remember that also P is going to be expressed in the same basis R, S, and W. Mu H squared plus mu R cos theta plus mu E R PS. This is the end. This is the most general expression you can find for the variation of the eccentricity. Whatever the P is, doesn't matter. So, how is this beneficial? Why do we care about doing the same thing for the 6 of them, which I'm going to project, by the way? Well, for example, this gives me a little more insight than just, if I add the perturbation, I integrate my equations of motion in ECI and then convert into orbital parameters, and I just look at that plot of E, and I have no idea. Well, this tells me that if I have a perturbation that projects into the radial and tangential component of the LVLH, those can affect my eccentricity. But if you turn on a thruster, for example, that it's, I erased that nice plot for once that I had a nice plot. If you turn on a thruster in the W direction, which is the normal to the orbit, you're not going to change the eccentricity at all. You can fire as hard as you want. It's not going to affect the eccentricity, right? So the same type of reasoning goes along for the other ones, where in some cases it's pretty obvious what kind of effect you're going to have on your orbital parameters if you turn on an engine, or if you have drag, or if you have something that projects in a certain way in some directions. Now, for example, before I show you all of them, so there is a differential equation like this, even uglier than this, for each orbital parameter. But an example, drag. We talked about drag last time. How would you look into the effect that drag has, again, on the eccentricity? And I'm not going to do the steps, okay? But the drag, I have to express it as a P, right? So what is my P for drag? It was -1/2 density ballistic coefficient. This is usually defined as CdA/m, so that you don't rewrite everything. Well, we had the relative velocity. Say that we neglect the velocity of the atmosphere. We do a lot of approximations as engineers, and in a class like this, I hope it's clear that if you don't use something like MATLAB at some point and you want to become serious about what's going on, you just, analytically speaking, there's so much you can do. So this is something that people do to look at drag. They say, well, if the atmosphere is going with the planet, yeah, it moves fast, but my satellite is 7 kilometers a second, so it's probably much faster. So I'm going to neglect it, so that this is my drag force, right? This was a VREL before, now it's just the velocity of the spacecraft. Okay, well then, if I want to use that equation, I have to express this perturbation in the LVLH basis. That's pretty easy, actually. Because this is -1/2 rho B. Let's see how I have it here. What is V squared? How do I write V squared? I'm going to leave it as it is. Another way to write this, remember from last time, it's writing V times normal V times the velocity vector itself. So how about I do this V, and then the velocity vector itself, I can write it as VR in the R direction plus Vs in the S direction, the usual stuff that we have done. And so in the end, you have 1 minus 1/2 rho B V VR in the R direction, and then you have this V Vs in the S direction. So what are these? This is my perturbation in that basis. This piece here that is multiplying R is PR, perturbation in the radial direction. And this is PS. That's what you do. Now for J2, next time, I am just going to show you the page of the book where they do this, because there is spherical trigonometry involved to find from the ECI expression of J2 that we have demonstrated for one component last time, to go into LVLH. It is possible, and it takes 4 pages of trigonometry, spherical trigonometry. So if you want, I can spend 3 lectures on that, but I think it's kind of pointless. All you need to know is these equations do take the perturbations in LVLH because it's just convenient. And now if you plug these expressions in there, where you see PR and PS, and you do another 2 pages of calculations, I'm not going to do it. So with drag from this, with that PR and that PS, you get the dE dt is, it looks quite nice actually, B rho V, the velocity, E plus cosine of theta. That's it. That's how your eccentricity is changing due to drag. Can you tell something about this? Well, not having this cosine of theta, theta again is the true anomaly, I would say, well, everything is positive here. The eccentricity is definitely a positive number. V is the normal velocity. Density cannot be negative. B is a positive quantity right there. So it's driving down my eccentricity, right? Yes?
So then with drag, dE dt is only that expression?
Yeah, that's it. Well,
added to the box thing?
No. This expression, when I substitute PR and PS, as I have them down there, and having fun with, some formulas, that's what you get. I have my notes. If you want, I can scan them. But so, as I said, these, if I didn't have the cosine of theta, I would say, well, my eccentricity is just going down, right? That's what is happening here. And go back to when we talked at the beginning about drag. Sputnik had a very low perigee and eventually circularized. That's what happens with drag. It circularizes your orbit. You can start with some eccentricity, then eventually what happens is that it kills the eccentricity and you become circular until you burn into the atmosphere and then goodbye. But that's really what happens. If you have, say that you start with a pretty eccentric orbit. I don't know how to do it here. Well, this is my planet, right? And you have a pretty eccentric orbit, say low perigee here and then high apogee. But the perigee is such that this is in atmosphere, right? It goes through the atmosphere. This is the way you want to look at it. Every time you come here at perigee, of course the drag is a continuous force, but you can say that you get the peak of the drag force at perigee because that's where you are the closest, which means the lowest, which means the highest density, and you're the fastest. So this force is at the peak down here, right? So if you just forget about everywhere else and you just say that you turn on the drag just here, it's like having an impulse. This is forcing, my imagination, but this is like having an impulse that slows me down. Hohmann or impulsive maneuvers, what do you do when at perigee you slow down? You're reducing the same major axis. And that's what is happening. Next time around, same major axis is going to be here. It's going to be here. It's going to be here. This becomes circular. And that is the equation that proves it for the eccentricity, except there is an oscillation there, yes, but that is always the same. Eventually, the trend will be to go down. So I think, do you have any questions for this? You know what? We're doing drag. Let me tell you what the other ones are for drag, because it's an important perturbation. So that would be the eccentricity. Now the same major axis, which I also did, dA dt, if you have drag, looks like this. We'll talk about integrating these equations next time, by the way. But for now, we just look at them and make some comments. Yeah. So there is still a term here that oscillates because there is this sine of theta, right? But there is a pretty steady term here where I see all positive quantities. Again, a cubed cannot be negative. These, well, unless you have a parabolic or hyperbolic flight, it's positive, everything. So my same major axis is going down, except the oscillation. What I'll do next time, I'll show you without derivations how these equations do average. There is a procedure to average them and basically remove every sine and cosine that you see and just focus on the trend. Because some of these equations do not have a trend. They don't change the orbital parameter in a steady way. They just oscillate. Some don't. So the d omega dt with drag is going to be pretty simple. Minus b rho v over the eccentricity sine of theta. The true anomaly is, guess, this is the Keplerian piece, right? This is always there. plus B rho V over E sine of theta. And then the other ones, what do you expect them to be? Just as intuition. Do you think these are going to change? Drag acts on the plane in LVLH, right? On the same orbital plane, right? And same major axis has to do with the shape of the orbit in the plane. Eccentricity has to do with the shape of the orbit in the plane. This as well, because it's where the eccentricity vector is pointing in that plane. This is the position of your satellite in that plane. These are the two that have to do with outside the plane. These things don't change. These equations are great. They give you insight about how the orientation of the orbit can change and how the shape can change due to perturbations. And again, that's how you can find the right inclinations for. Let me show you them. Yeah. Oh, yes.
Is that dt h of r squared?
Yes. Yes. Thank you. Yes.
The last velocity in the dA over dt equation,
It's a VR.
is that v sub something, or is that
Yeah, it's VR. Sorry, VR. Radial. Again, you can forget about the. So let me show you the general form for all of them, right? You don't have to go through the exercise of always writing the perturbation and then substitute and do some simplifications. It's usually convenient. You can leave them as they are and just enter in the equations PR, PS, and PW where needed. It's just the sum of them. It's easy to see what the effect is if you substitute. Yes?
The eccentricity is going down with time, with drag, then how do we use it in those other equations? With the
You have to integrate all these equations. They go together. You have to, again, we're not going to do integration of them today, but imagine they are like the same equations that you've had so far, that you have integrated in ODE 45. Same thing here. You will have to integrate them numerically, right? You have to do it all together. You can't solve one separate from the other. So in the same MATLAB function, you will have to integrate dA dt, dE dt, dI dt, d big omega, all of them in parallel, and substitute, what you need there. Yep. So these are the ones. The only one that, I don't know if the book gives you that one, but I'll give it to you. It's dA dt, because they give you dH, the rate of change of the angular momentum, which is equivalent, but I like dA dt, so I wrote it down here, and you may want to write it down as well, if I can find it. So those are 5 of them. The one that is missing there is this one. dA dt is 2a squared e sine of the true anomaly over h pr plus 2a squared p h r ps. P is the semi-latus rectum. It's what is it? I think it's a 1 minus e squared. Think so? It's your position at 90 degrees, true anomaly 90 degrees. The radius at true anomaly 90 degrees. So these are the equations. All of them, as you can see, have a bunch of variables, PR, PS. The eccentricity is only affected by radial and tangential component. The true anomaly, same story. These two, as we said, drag doesn't have any effect. If you want to change the right ascension of the ascending node and the inclination, you need to have an out-of-plane acceleration. And J2 does that, right? Yeah, next time I'll look at the average equations, but that's J2 will come into these as a non-zero PW, and it creates a change in those. And this is the last one, which is the only one that has an effect from all of them. Okay? What else can I tell you that you want to hear? You have any questions? I was going to leave a few more minutes for the tests, but the tests are not coming. So, you have any questions on these? So, at some point, what I'm going to ask you to do for an uncollected homework that most likely will become part of the homework, so you better do it, is integrate this. So imagine start thinking about how do you do this? I give you initial orbital parameters, the 6 of them, at time 0. So in principle it will be, you have initial conditions for your differential equations and you integrate them. But everything you see in there requires you to do something. You need to compute the radius, you need to compute the velocity, you need to compute the angular momentum. So inside your function that integrates these differential equations, you will have to continuously convert into Cartesian coordinates, not exactly entirely convert into Cartesian coordinates, but you need to find a way to compute r, because r it's there. V, do we see V? All the V's are simplified. So basically r and h. Okay? Here it is. All right, guys. I'll see you next time.